In our project, we will explore the use of machine learning in stock price prediction. The goal of our project is to compare the performance of different machine learning approaches used to predict stock prices. Factors compared will include the time and the computational resources to train the models, as well as their accuracy and how well they generalize to new stocks. Models compared will include linear, multi-layer perceptron, LSTM, RNN, and GRU. All the data gathered is using the Y-Finance library, which was downloaded from Yahoo Finance. Variables include daily high, daily low, opening closing prices, and daily number of trades. The models were trained using Apple stock history, where a certain amount was used for training and the remaining data was held out to test how the model would do with new data. Our initial hypotheses are as follows. We believe that linear regression will be too simple to accurately predict stock prices. We believe MLP will be a slight improvement due to its increased number of layers, but not ideal. We believe simple RNN will also have issues due to the vanishing gradient problem. Next, we believe that LSTM RNN will overcome the vanishing gradient problem and be a good stock price predictor. We believe that GRU will further improve on LSTM with better accuracy and training efficiency. Finally, we will use the Facebook Profit library, which we believe will be the most accurate because it is pre-trained. We predict that our models will be able to identify the general stock patterns such as spikes in the summer and winter months, as shown by Amazon stock. We predict that less predictable stocks such as GameStop and Roblox will not follow the model as well. For example, if a stock were to have an unexpected spike that the model does not follow, then the model would be off from that point going forwards. At least that is our hypothesis. For linear and MLP, custom models were created using Python's Lightning module. The linear model has a single linear layer and a standard forward loss training step and other functions. Pre-processing is performed. Next, the data is split into training, validation, and testing with 70%, 10%, and 10% respectively. Early stop policies were implemented to prevent overfitting. MLP has a similar architecture to linear, except we added an additional ReLU and linear layer. Pre-processing was done similarly, and the same training and validation splits were used. While for the remaining RNN, LSTM, and GRU models, we used the built-in PyTorch, RNN, LSTM, and GRU models respectively. The remaining loss, training, and validation steps were similar. For RNN, a sequence length of 10 days was used in an attempt to have it better generalize over longer periods of time, rather than just one day that we used for linear and MLP. In addition, 95% of the data was used for training in hopes of achieving higher accuracy. Similar early stop callback and training loops were used for all the models. The LSTM model was designed similarly, taking a hidden size and number of stacked layers parameters. LSTM and GRU use different data preprocessing techniques using the min-max scaler. In addition, 95% training data was used for these models to achieve desired accuracy. GRU was very similar to LSTM, also taking a hidden size and number of stacked layers parameters. The linear model was much more effective than we predicted. Stock data is typically represented as a linear function, so it makes sense that the model performed well. The green area is where the model was trained, the yellow area was validation, and the red area was testing. We can see the model performance remained consistent throughout even the testing area, greatly surpassing our expectations. The model does not appear to be overfit, as it did not exactly memorize points on the stock. There was some variance. The input features open, close, high, and low are highly correlated with the target. This could explain why the linear model worked so well. Since our MLP model has more layers, it was able to be trained more quickly, but it was also more quickly prone to overfitting. So we had to use early stop policies, and we ended up only using the first few epochs. Similarly to the linear model, MLP exceeded our expectations by being able to accurately predict the stock price beyond the training data. We believe the model is not too overfit, as similar to linear, it's not exactly predicting the price and has some variance. There is still some concern that the model is overfit and may not do well in predicting the future stock prices. Both the linear and MLP models were able to accurately generalize to new stocks, even if they were unpredictable and had not been seen by the training data. As predicted, the simple RNN model was prone to the vanishing gradient problem. The validation error of the RNN did not go down despite our best efforts to provide a higher look-back window and greater training dataset percentage. As we can see with the testing data, the RNN model was unable to accurately predict the stock price. It eventually hit a point where the stock price flattened out because it was unable to gain new information far back enough in time. We believe this is the point where the gradient approached zero. And we can see the difference in stock price increase as the model fails. Our LTSM model was able to overcome the vanishing gradient problem. LTSM is able to look further back into the past. As we can see, the validation error did decrease over time, suggesting an accurate model. The model was able to be trained over a large number of epochs without getting overfed. We can see the model was able to accurately predict the training data, and it also generalized well to testing the same stock, though with some variance. The model would still be prone to some inaccuracies when there'd be large unexpected jumps or drops in the stock price. LSTM also generalized well to stocks it had not seen before. The issue with LSTM was that we had to allocate 95% of the dataset for training to get an accurate result. In addition, we only provided more recent data of the last 10 years of the Apple stock as opposed to the stock's total history. In summary, LSTM performed very well when trained properly, but it only needed the most recent data, and it needed to use almost all of that data for training. This suggests that LSTM has the potential to predict stocks into the future in the short term, given recent data, but possibly not into the long term, as it could be off-centered. These results still suggest that LSTM and GRU would generalize better for future predictions than linear and MLP, as they do not exactly memorize points and might be more flexible to future patterns. As predicted, Facebook Profit was the most accurate compared to our standard models. Since it was pre-trained on a variety of stocks, it performed roughly just as well on any stock we threw at it, and was quite good at generalizing to unique or variable stocks like Roblox or GameStop. Profit was also able to make sound predictions farther into the future because it considers the weekly, yearly, and other financial trends, as well as current news events and any other data that Facebook provided when training. Our Streamlit app allows the user to select from a variety of stocks, and then the stock data will automatically update. The raw data as well as the raw time series data for the stock is displayed. The stock forecasts for our standard models are shown. The user is able to toggle the legend to see linear, MLP, LSTM, and GRU model predictions. The stock will automatically update when a different stock is selected. Facebook Profit will also automatically predict 1 to 4 years into the future of the same stock that was provided at the top. We see the actual stock data in black and the predicted stock data in blue. There's also a range of how accurate the prediction may be. We can use the slider to see farther into the future or change the range of the stock. Facebook Profit also can identify forecast components, which is part of how it can be so accurate, including the overall trend, the weekly trend, and the yearly trend, identifying those summer and holiday bumps. Overall, the accuracy of our standard models from linear to GRU was limited by the fact that they were only provided stock values and not external factors such as news or public opinion. For unpredictable stocks like GameStop, we saw how a massive spike could not be fully predicted by these simple models, with the actual spike being larger than the usual prediction from GRU and LSTM and the other models. In conclusion, the linear model received a very accurate prediction while using the least computational resources. MLP was also accurate, needing more layers but fewer time to train. Simple RNN was not appropriate for the task due to the vanishing gradient problem. And finally, even though LSTM and GRU did not provide the advantage we expected, they may be appropriate for forecasting stock prices into the future as opposed to simply recreating stocks they were not trained on.